and reasons for my heart to. Anyway, I hit that on guitar like boom, like with just an open E string.
He was more of like a.
He was more. What's the word for that? Like the singer-song or folk style a little bit. Yeah. Yeah, I'm not that good. I can go bow, bow, bow. That's where I'm at. Other people tell me, oh, you're so good at guitar. I'm like, your standards are really low. Because I am not that good at guitar. Well, let's pray and we'll talk and we'll get started. Father, thank you for today. Thank you for chemistry. And that you've given us this amazing insight into how the universe works. How you hold everything together and arrange it. It is truly amazing, Father. Help us as we study to really learn these things and to have good recall, not only for midterms coming up, but Father, for any classes we'll have the rest of our lives. We pray this in Jesus' name. Amen. So, as I was saying a minute ago, midterm, starting next week on the 5th, it'll open up. And it'll run all the way through spring break. So you'll have as much time as you want to take it. Of course, you only have 2 hours. Well, you don't know this because you've never taken one. Well, I guess you did the final.
I did the final.
Yeah. So you'll have a 2-hour window to open it. You can print it out or you can do it by hand. But I do need to see all the work by hand and then take a picture and upload it to me. Okay. Okay, so practice for that, it's going to be chapter 9, so practice for that is just do the odd problems in chapter 9. If some of them are weird, you know I'm not going to give you weird ones. You're looking for the ones that look like the practice problems. Those are the ones that I'm going to, work from. So, okay. Well, I feel out of breath. Where did we leave off, my friend?
I think we did one last problem.
Okay, we did those partial pressure problems. Okay. Okay, so this will be practice problem 9.15, pressure of a mixture of gases. Okay. I gotta get my head back in this. It's been elsewhere today. A gas mixture used for anesthesia. We did this one, didn't we?
I think so.
We did the anesthesia. Okay. All right, collection of gases over water. New topic. A simple way to collect gases that do not react with water is to capture them in a bottle that has been filled with water and invert it into a dish filled with water. The pressure of the gas inside the bottle can be made equal to the air pressure outside by raising or lowering the bottle. When the water level is the same both inside and outside the bottle, the pressure of the gas will be equal. So here's what it's saying. Simple way to collect gases that do not react with water is, it only works if they don't react with it, right? So, and plenty do, including carbon dioxide, by the way. Fun fact, if you ever load carbon dioxide into water, especially with a pH measuring solution into it, it forms carbonic acid. Just like it's what's happening in your blood, and it will change pH and all that. So here, fun thing you didn't necessarily know, but there it is. Collect them in a bottle that has been filled with water, and then invert it into a dish full of water. Can you give us a picture of this? Not so much. Here's the bottom line. I've got this this deal, okay, and it's got a stopper in it, and I've got some water, and I've got my gases, okay. Now, presumably this is not going to be at 1 atmosphere, or whatever the general atmospheric pressure is. But if I take this same thing and I invert it, right, I'm going to have water on the bottom. Now if I take this and I put it in a dish of water and uncork it, now the water's free to go in and out. And if I want to adjust this so that the air pressure is the same inside and outside, then I just lift it or raise it until the water line is the same everywhere. And then I'll know I'm at whatever that present condition is. If this is 1 atmosphere, then it'll be 1 atmosphere. If it's 2 atmospheres, it'll be 2 atmospheres. So, there we go. What are we doing with this? All that was so that we could understand this. Now, I didn't finish reading. When the water level is the same both inside and outside the bottle, the pressure of the gas is equal to the atmospheric pressure, which can be measured with a barometer. Okay. However, there is another factor we must consider when measuring the pressure of the gas by this method. It's water vapor, right? Water evaporates and there is always gaseous water or water vapor above a sample of liquid water. As a gas is collected over water, it becomes saturated with water vapor, and the total pressure of the mixture equals the partial pressure of the gas plus the partial pressure of the water vapor. The pressure of the pure gas is therefore equal to the total pressure minus the pressure of the water vapor. This is referred to as the quote-unquote dry gas pressure. That is the pressure of the gas only, without the water vapor. The vapor pressure of water, which is the pressure exerted by water vapor in equilibrium with liquid water in a closed container, depends on the temperature. More detailed information on the temperature dependence of water vapor can be found in Table 9.2. The vapor pressure will be discussed in more detail in the next chapter on liquids. Okay, so that's our background information. What is it really wanting us to say inside of here? The pressure inside P of the container equals, right, the P of the gas and the P of H2O vapor, okay? And we can calculate this. And especially based on temperature. So that's the conceptual component of it. We're going to need all these things because it's going to have us calculating the pressure of the gas. So here we go. This is example 9.16. If 0.200 liters of argon is collected over water at a temperature of 26 degrees centigrade, and a pressure of 750 torr in a system like we've been describing, what is the partial pressure of argon? So we're going to find partial pressure of argon. Okay. So how do we do this? According to Dalton's law, the total pressure in the bottle at 750 torr is the sum of the partial pressures of argon plus the partial pressure of water. Okay, great, we know that. So P total equals P of argon plus P of H2O, and by the way, all of that equals 750 torr. Okay. Rearranging this equation to solve for the partial pressure of argon. Why are they acting like we don't know how to do this? I don't know. There's a table that you need that you don't have.
Okay. Because the pressure of water.
Let me go. I'm gonna take a second. I'm gonna give you the partial pressure of the water off this table, and I'm gonna go make a copy of this table, and you do the work, and we'll come back and do it. So we are at 26 degrees centigrade. 26 degrees. At 26 degrees centigrade, partial pressure in torr of water looks to be 25.2. At 26 degrees centigrade. So this one's about as easy to get, so I'm going to make a photocopy of this real quick.
Okay.
temperature. Okay, so P total is 750 torr, right? So 750 torr minus 25.2 torr equals 724.8 torr, right?
Yes.
Okay, so there we go. Feels like a waste of our time. Let's do the next one. A sample of oxygen collected over water at a temperature of 29 degrees centigrade and a pressure of 764 torr has a volume of 0.560 liters. What volume would the dry oxygen from this sample have under the same conditions of temperature? So let me erase all this. This is a little better problem. I like this one. Okay, let's write it down again. So we've got O2 over water, right? At 29.0 degrees centigrade. By the way, what's the partial pressure? Well, we'll get to that in a second. And a pressure of 764 torr and a volume of 0.560 liters. Okay. All right, so give me my P total equals equals 764 torr. Which equals my pressure of O2 plus, what is my pressure of water at 29 degrees centigrade?
30 torr.
Plus 30 torr, right? And so when I solve this, my partial pressure of my PO2 equals 734 torr, right?
Yeah.
Okay. Now it's wanting us to take that a step further, and it says what volume, find the volume for the dry oxygen from this sample under the same conditions of temperature. So we got a PV equals nRT situation, right? I'm solving for V, so I need V equals nRT over P. My P, I know it's 734, right?
Yeah.
I know I'm going to want to convert this to atmospheres because I like the one form over all others. So I need to divide this by 760, right?
So you multiply.
So I can multiply by 760. So I'm going to go 760 torr per 1 atmosphere, okay? I'm going to multiply that by my 0.0821 times my temperature, which is 29 degrees centigrade plus 273.15. You do that math.
That's 302.15.
Say it again.
302.15.
0.15 degrees Kelvin. Okay, now I got to do it by my number of moles, right? Okay, so that'll be the hard part. Is I've got, where am I at here? Okay, so how am I solving for my number of moles? That's the question. What do we have to help us get there? Well, we know this is the size, this is our deal, right?
Mm-hmm.
Okay, so if I have 0.56 liters, and I know that 1 mole occupies 22.4, right?
Mm-hmm.
per mole, right? So I can invert that, right? Then when I divide this by this, that's going to tell me the total number of moles, and then I can use my mole fraction, which I know based on my partial pressures. So let's do 0.56 divided by 22.4. That'll give me the number of moles of gas total.
0.025.
0. What?
0.25.
0.25 moles. That's moles total. I need the percentage of that. So my total pressure here was 764 torr. Come on phone, what are you doing? My total number of, or my partial pressure of this was 734, so I divide 734 by 764, and that's 0.9607, blah, 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 blah. When I multiply that by my total number of moles, then I get an answer of 0.024 moles. You get the same? Okay, just to recap, because I didn't write all this out, I just kind of talked through it. But the process here is, I know I have however many moles I have, I know they're fitting in 0.560 liters, right? I think I made a mistake. Because I'm not at standard temperature pressure, am I?
Wouldn't it be easy if we do P1 equals P2?
Say it again.
If we do like pressure 1 times volume 1 equals pressure 2 times volume 2.
Okay, so let's go P1 over P2 equals V1 over V2.
Yeah.
You're doing this to get to,
See, that's volume 2.
oh, I'm sure it probably is easier.
Yes.
Yeah. But my volume stays the same, right?
I don't know.
Volume stays the same.
Or is pressure 2 the moles?
Yeah. Yeah, my volume stays the same. So, boy, I should have worked this one out, maybe I shouldn't I? Real quick, I want to run this and see how far off it puts me, and then we'll go backwards if we need to. So this would have, if we went with this, it'd be times that. So we go 760 times 0.0821 times 0.024 divided by 734 equals 100. Oh, it's asking volume, isn't it? It's not asking pressure. We're going back to your method. Ignore everything I just said and did, because my head went on a wild goose chase. Required way more calculations than we needed. Okay, so coming back at this. P1 over P2 equals V1 over V2, right? So my pressure 1 is 734 torr. Now my pressure 2 is,
And then I don't know if they asking the pressure.
well, it's asking the volume. Let's read the question again. The sample of oxygen collected over water at a temperature of 29 degrees centigrade and a pressure of 764 torr has a volume of 0.56 liters. What volume would the dry oxygen from this sample have under the same conditions? Oh, it's not hard. Okay, so my Okay, that's not hard. We got it. We just, okay, my P1, we're going to call my 764. 764 is my initial, right? My complete. I don't want it for my complete. I only want it for this, which was 734 torr, right? Okay. Which equals my V1 over my V2. My V1 was 0.560 liters. I just have to cross multiply and divide. We both made that too hard. Let's try it again. 734 times 0.56 divided by 764 equals 0.538 liters, which should be the correct answer. Yeah, that's a lot better. No doubt I could have got there the more complicated way, but I'm glad we didn't have to. All right. Let's do one more like that I'm going to make up on the fly, just because we made such a mess of that. I made such a mess of that. Okay, so let's do, I don't know, let's do neon. Neon, let's do 0.82 liters at, let's go 27 degrees centigrade. Yeah? Do I need more information than that?
The pressure for the system.
And my pressure of my system is going to be 780 torr. Okay. So, my pressure total equals my pressure of neon plus what's the pressure of water at 27 degrees centigrade?
26.7.
26.7 torr. Okay. So and this equals 780 torr. So when I do that math, I get 753.7, is that right?
Yeah.
Okay. Now, I had, our formula is P1 over P2 equals V1 over V2. My pressure 1 was 780 torr.
Sorry, the pressure here is 753.3.
Okay, thank you. Did that wrong, didn't I? Pressure 780 torr. My pressure 2 is 753.3 torr. Right, my volume 1 is 0.82 liters. My volume 2 is what I'm solving for. So now I will cross multiply and divide. I get 0.792 liters. You get that?
Yep.
Okay. All right, good. We're confident that we can do this in the future. All right. Next section, chemical stoichiometry in gases. Chemical stoichiometry describes the quantitative relationships between reactants and products in chemical reactions. We've previously measured quantities of reactants and products using masses for solids and volumes in conjunction with the molarity for solutions. Now we can use gas volumes to indicate quantities. If we know the volume, pressure, and temperature of a gas, we can use the ideal gas equation to calculate how many moles of the gas are present. If we know how many moles of a gas are involved, we can calculate the volume of a gas at any temperature and pressure. Let's go back and think about Avogadro's law. Sometimes we can take advantage of a simplifying feature of the stoichiometry of gases that solids and solutions do not exhibit. All gases that show ideal behavior contain the same number of molecules in the same volume. Thus, the ratios of volumes of gases involved in a chemical reaction are given by the coefficients in the equations for the reaction, provided the gas volumes are measured at the same temperature and pressure. We can extend Avogadro's law that the volume of a gas is directly proportional to the number of moles of the gas to chemical reactions with gases. Gases combine or react in definite and simple proportions by volume, provided that all gas volumes are measured at the same temperature and pressure. For example, since nitrogen and hydrogen gases react to produce ammonia gas, according to the following formula, which is N2 gas plus 3H2 gas yields 2 NH3 gas. A given volume of nitrogen reacts with 3 times the volume of hydrogen gas to produce 2 times that volume of ammonia gas, if pressure and volume remain constant. The explanation for this is illustrated in blah, blah, blah. According to Avogadro's law, equal volumes of gaseous N2, H2, and NH3 at the same temperature and pressure contain the same number of molecules, because 1 molecule of N2 reacts with 3 molecules of H2 to produce 2 molecules of NH3. The volume of H2 required is 3 times the volume of N2, and the volume of NH3 produced is 2 times the volume of N2. Great, lots of words. So here's our problem. Propane. C3H8 gas is used in gas grills to provide the heat for cooking. What volume of oxygen gas at 25 degrees centigrade and 760 torr is required to react with a 2.7 liter sample of propane. Okay. So there's going to be a couple of steps to this, right? One, we got to think about the combustion reaction between propane and oxygen, right? To get a mole-mole ratio. So C3H8 plus O2 is going to yield CO2
And water.
plus H2O, right? I've got 8 here, right? And it's going to produce half as many here, right? So 4. All right, those balance out. I've got 3 here, so I need 3 here, right? So carbon's balanced, hydrogen's balanced, oxygen right now I would need 4, and I would need 6, so that's 10. So that would put a 10 here.
5?
Oh, I'm sorry, thank you very much. Wow, that was special. Okay, so we'll do a quick accounting. I've got 3, I've got 3. I've got 8, I've got 8. I've got 4 and 6 is 10. You get 5 times 2 is 10. This is balanced. Okay. So I know that for every 1 mole, when I think about my mole-mole ratio, I've got a 1 to 5 ratio of carbon, of methane or propane to oxygen, right? Okay. So all I'm going to, when I think about solving this problem, I want to find the volume of oxygen. If I can, because it's a 1 to 5 ratio, whatever the volume.
Propane.
Is that all it's asking?
2 points.
Yeah. Is it that simple?
It looks like.
It's that simple. Yeah.
Just gonna multiply by 5?
Yeah.
By 1?
Yeah. So, yeah, my volume is 2.7 liters of propane. Times, I want to do 1 mole of propane. Or actually, I want to cross out. I'm going to do 5 moles of O2 over 1 mole of propane, C3H8. When I do that, my propane is going to cancel. My moles are going to cancel. I'm going to be left with liters of oxygen, right?
Mm-hmm.
That should be it. Yeah. So, 2.7 times 5 is
13.5.
13.5. That's it. I wanted that to be harder. I don't know why. Something probably wrong with me. All right, let's try the next one. Maybe it will be harder. All right. Next problem on here. An acetylene tank for an oxyacetylene welding torch provides 9,340 liters of C2H2 at 0 degrees centigrade and 1 atmosphere. How many tanks of oxygen, each providing so 1 tank of oxygen provides 7.00 times 10 to the 3rd liters of O2 at 0 degrees centigrade and 1 atmosphere, right? So how many tanks of oxygen for 1 tank of acetylene? So before we worry about anything else, we're going to go ahead and look at this combustion reaction. So we got C2H2 plus O2 is going to yield CO2 plus H2O. Okay, so I've got 2 carbons here, so I need to put a 2 in front of that. I've got 2 hydrogens here, so that's balanced, right? So this, in terms of oxygen, this is going to give me 1. This is going to give me 4, so that's 5, right? 5 divided by, when I'm dealing with this, would give me 2.5, right? So I'd get, if I were to rewrite this, I'd get C2H2 plus 2.5 O2 will yield 2 CO2. 2 is 4 plus 1 is 5. That balance, okay? And this should work out for what we need, I believe. Okay, so now that we know that, let's write out our ratio. It's going to be a 1 to 2.5, right? Now that's for moles or volumes, okay? Now, let's check what we got here. We've got differences in liters, right? So I've got 9,340 liters of acetylene, right? So of C2H2. I want to get to my liters of O2, right? So I need 2.5 times as many, right? So I'm going to go 2.5 liters of O2 to 1 liter of H2, right? That's going to leave me with my liters of O2, and then what I need to do is divide by however many liters there are in a thing here, and that'll tell me how many tanks I have. So I'm going to go ahead and do the first step. 9340 times 2.5 equals 23,350 liters of O2, right? Now, all I need to do is multiply that by 1 tank of O2 over 7.00 times 10 to the third. Since I'm doing it on a little phone calculator, I'm just going to go 1, 2, 3, 7,000 liters of O2. Okay, so I go 23,350 divided by 7,000, and that equals basically 3 1/3 tanks. So let's see what, that's exactly what the book has. Life is good. Okay. Let's do another problem. Okay. Where are we at? This is sample problem 9.18. Okay. Ammonia is an important fertilizer and industrial chemical. Suppose that a volume of 683 billion cubic feet of gaseous ammonia. So, what's it? What? We're at thousands, we're at millions, we're at billions, right? Cubic feet. That's what we use all the time. Of gaseous ammonia, so NH3. By the way, the book is not spelling it out like this. They're literally writing out the words. Measured at 25 degrees centigrade and 1 atmosphere, was manufactured. What volume of hydrogen gas measured under these same conditions was required to produce this? So, to get ammonia, I need N2 plus 3H2, which is going to yield 2NH3. So I want to know what volume of, was it hydrogen gas that I wanted? What volume of hydrogen gas under the same conditions was required to produce that much of that? So this is that much of ammonia gas. I look at my mole-mole ratio. I need 3H2 to every 2 of those. This is not that hard. Again, 683, 1, 2, 3, 1, 2, 3, 1, 2, 3 of NH3 gas, right? Times, I need 3 moles of H2 gas for every 2 moles of NH3 gas. Right, so that's going to give me my cubic feet of H2 gas, because these are going to cancel. So, there we go. Let's do it. 683. 1, 2, 3, 1, 2, 3, 1, 2, 3. This phone. Get 1,024,500 million.
Yeah.
Yeah. Okay, ridiculous numbers. For a practice problem, why you're dealing with cubic feet and in the trillions, I do not know. But there we are. Let's do the next one. What volume of oxygen gas measured at 25 degrees centigrade and 760 torr is required to react with 17.0 liters of C2H4 gas? We're going to find O2. Okay. So we got to begin with the reaction. C2H4 plus O2 will yield CO2 plus H2O. I got 2, so I need 2. I've got 4, so I need 2. This gives me 2 plus 4 is 6. Divided by 2 is 3. Double check. 2, 2, 4, 4, 6, 4, and 2 is 6. That's my thing. Now my ratio I need is a 1 to 3 ratio, right? Okay. So if I had 17 liters, I need 17 times 3, right? So what do you get? 51 liters, right? Okay. So just to spell that out, it's 17 liters of C2H4 times, the ratio is going to be 3 liters of O2 over 1 liter of C2H4. That gets me my, sorry, it's 51 liters, right?
Yeah.
51 liters of O2. Okay, there we go. Next one. What volume of hydrogen gas at 27 degrees centigrade and 723 torr may be prepared by the reaction of 8.88 grams of gallium with an excess of hydrochloric acid? Okay. So our reaction looks like this. We've got gallium, solid, plus HCl, aqueous, right? Is going to yield, should be GaCl plus H2 gas. This should be aqueous, right? Okay. Now, just the question is, what are our, how many bonds is gallium going to make?
Gallium?
Yeah.
5.
5? Surely not. You see where it's at.
3.
gallium is going to make 3, so what we expect to find here is GaCl3, which means I would need 3 here, right? Which would mean this would produce 1.5 of this, right?
Yeah.
We don't like that. So what we're going to do is double the whole thing, right? So I'm going to get 2 Ga solid plus 6 HCl aqueous yields 2 GaCl3 plus 3 H2 gas. Is that right? That looks right. Okay. What are we trying? We're trying to find just the volume of hydrogen gas at those conditions. Okay. Now we have 8.88 grams of gallium, right? Okay. So I've got 8.88 grams of gallium. Now I need to know how many moles. I got to get that to moles, right? Times, what's my molar mass for gallium?
It's 69.723.
69.723 grams per 1 mole, right? Now I know that I need I need 2 moles, right? Well, we'll stay with this. We'll figure out how many. I just worked myself into a mess. Oh, yeah, I can make this a lot easier than that. I can go right into my mole-mole ratio, right? So I'm going to have 2 moles of gallium for every 3 moles of H2. This is going to give me moles of H2, which then I can use to plug in and find the volume, right? So, all right. When I do this math, you get a calculator, proper calculator. You get 0.191 moles
Yeah.
of H2. Yes. Okay. All right. Now I just need to know what my volume is, right? So I should be able to use PV equals nRT to solve for that. I'm looking for my volume, so I need nRT over P. So I've got 0.191 moles times 0.0821 times my temperature of 27 plus 300.15 degrees Kelvin. Okay, and I need all this over my pressure, which is 723 torr over 760 torr per atmosphere. Okay, so go ahead and run that math. So what'd you get?
4.94795.
Okay. Very good. Good. Let's try this next one. them while they're building up to putting these pieces together. Yes, that's good. Sulfur dioxide is an intermediate in the preparation of sulfuric acid. What volume of SO2 at 343 degrees centigrade and 1.21 atmospheres is produced by burning 1.00 kilogram of sulfur gas, or sulfur solid, excuse me, plus excess O2. Okay. So take a look at where sulfur's at. Actually, I guess we don't need to. We already know what the product's going to be, don't we? So we've got, our formula is this. We've got S solid plus O2 gas yields SO2. Right? This has got to be S4, doesn't it? Does that seem right? So if we want to make 4, no.
That's two, isn't it?
Let me see something.
Isn't the same as oxygen?
Yeah. Should I have? Okay. That seem right?
Yeah.
Okay. All right. Well, let's do it. So we've got 1 kilogram, right?
Mm-hmm.
So 1 kilogram times. I need the formula mass for sulfur 2. How much is it for 1 atom?
32.065.
So 64.
0.13.
64.13 grams per mole.
Yeah.
Okay. All right, times. That'll put me into moles. This is moles of S2 solid, right?
Mm-hmm.
Now I need to go from S2 solid to 2 SO2. So I'm going to go 1 mole of SO2, or I'm sorry, S2 solid, to 2 moles of SO2, right?
Yeah.
Oh, yep, that's right. Okay, so hopefully we've done this correctly. So 1,000 times 2 divided by 64.13 equals,
31.19.
yeah, that's not what they got.
But that's the mole.
That gets me the moles, right?
Yeah.
Okay, I need to find volume.
Yeah.
So let's keep going. Well, actually, I did need that, didn't I? So it's 31 point, 31.19 moles. Is that right?
Mm-hmm.
Okay. So now I need to do PV equals nRT because I'm trying to solve for volume.
Yeah.
All right. So volume equals nRT over P. Okay. So my number of moles is 31.19 moles times 0.0821 times temperature of, holy moly, 343 plus 287.15, 630.15.
Mm-hmm.
Okay. Okay, that's nRT, and I need to put all of this over my pressure, which is 1.21 atmospheres. Okay, so let's do it. 31.19 times 0.0821 times 630.5 divided by 1.21. And we got the right answer. Equals 1.3 times 10 to the third liters. Right?
Yeah.
Okay. Very good. Where are we at? Well, we better keep going. Okay. Effusion and diffusion of gases. Go ahead and erase this. Everything. Got less than 20 minutes. Let's see what we can do. Okay. If you have ever been in a room when a piping hot pizza was delivered, you have been made aware of the fact that gaseous molecules can quickly spread throughout a room, as evidenced by the pleasant aroma that soon reaches your nose. Although gaseous molecules travel at tremendous speeds, hundreds of meters per second, they collide with other gaseous molecules and travel in many different directions before reaching the desired target. At room temperature, a gaseous molecule will experience billions of collisions per second. The mean free path of the average distance a molecule travels between collisions. The mean free path is the average distance a molecule travels between collisions. The mean free path increases with decreasing pressure. Makes sense. In general, the mean free path for a gaseous molecule will be hundreds of times the diameter of the molecule. In general, we know that when a sample of gas is introduced to one part of a closed container, its molecules very quickly disperse throughout the container. This process, by which molecules disperse in space, is response to the difference in concentration. It's called diffusion. The gaseous atoms or molecules are, of course, unaware of any concentration gradient. They simply move randomly. Regions of higher concentration have more particles than regions of lower concentrations, so the net movement of each species is from high to low concentrations. In the closed environment, diffusion will ultimately result in equal concentrations of gas throughout. Gaseous atoms and molecules continue to move, but since their concentrations are the same in both bulbs, the rates of transfer between the bulbs are equal, no net transfer. I'm joking. All right. We are often interested in the rate of diffusion. amount of gas passing through the sum area per unit time. The rate of diffusion is the amount of gas passing through an area over the unit of time. Diffusion rate depends on several factors: the concentration gradient, the increase or decrease in concentration from one point to another, the amount of surface area available for diffusion, and the distance the particles must travel. Note also that the time required for diffusion to occur is inversely proportional to the rate of diffusion. As shown in the rate diffusion equation. Okay, great. Process involving movement of gaseous species similar to diffusion is effusion, escape of gas molecules through a tiny hole such as a pinhole in a balloon or a vacuum. Although diffusion and effusion rates both depend on molar mass of the gas involved, their rates are not equal. However, the ratios of their rates are the same. The mixture of gases in a container with porous walls, the gases diffuse through the small openings in the walls. The lighter gases pass through the small openings more rapidly and at a higher rate than the heavier ones. Thomas Graham studied the rates of effusion of different gases and formulated what's called Graham's law of effusion. The rate of diffusion of the gas is inversely proportional to the square root of the mass of its particles. So here's his law. It says rate of diffusion equals inverse of the square root of its mass. Okay. This means that if two gases, A and B, are at the same temperature and pressure, the ratio of their rates of fusion is inversely proportional to the rates of the square roots of the masses of their particles. Oh. This means that if two gases, A and B, are at the same temperature and pressure, the ratio of their fusion rates is inversely proportional to the ratio of the square roots of the masses of their particles.
I think the molar mass B should be on top.
Yep, exactly. Okay. Calculate the ratio of the rate of diffusion. Calculate the ratio of the rate of effusion of hydrogen to the rate of effusion of oxygen. So we're going to compare hydrogen and oxygen, right? So, great. Just wants a ratio, right? So we're looking at, let's do H2 to O2, right? So to do that, I need O2 up here, which is what, 16.02, so 32.04 or 32.02?
I think 32.02.
2, good, and this should simply be 2, right? So square root of 32.02 over the square root of 2 4-to-1 ratio. Okay. Well, let's try another one. Okay. At a particular pressure and temperature, nitrogen gas diffuses at a rate of 79 milliliters per second. Under the same conditions, what rate will sulfur dioxide diffuse at? Okay, so I know that that's going to be 79 milliliters per second over rate for SO2, and I know that this is going to equal SO2 mass over the nitrogen mass, right? Okay. Right. So now I just need to find what's my molar mass for nitrogen gas.
It's 40 times 2 is going to be
28. 28 point what?
0.14.
0.14. Okay. And I need it for SO2. Molar mass of sulfur.
It's 32.065.
32.065 plus 32.1, so 64.1, let's call it 64.2. Right? Okay, so cross multiply and divide. So 79 times square root of 28.14 divided by the square root of 64.2. Give me a syntax error. What'd you get?
I'm doing
Okay.
I got 52.19.
Sorry. It's 52 milliliters per second. Okay. Good. All right, we will pick up next time. Make a note for me, okay? Sample problem 9.21. That's where we'll pick up next time.
Sample problem 92.
Sample problem 9.21. That's going to be where we pick up. All right. Don't forget, midterm opening up next Wednesday. So we'll have one more lecture before that. That's it.